Let's talk about blockchain technology. Now, there's no single blockchain technology. There's a lot of different technologies. There's a lot of different blockchains. And so we'll talk about some of the principles that define common characteristics of blockchains. So some components, often blockchains are decentralized so that no one single entity controls the data. This is in comparison to something like a traditional bank. Like Bank of America has a database where they store all of their transactions. And so they control it end to end, and that can work really well. That's not necessarily a problem. With something like Bitcoin, that blockchain is distributed so that thousands or millions of people can store a copy of that database. And everyone around participating in that blockchain has to agree that the transactions are valid. So decentralization can be very important. Immutability means that you can't change it. Once a record has been stored on the blockchain, there's no going back and editing it. So this provides some assurance that the data has integrity, the chain has integrity. We'll see how this works and how you can verify, like, oh, somebody tried to change data on the blockchain. Bank of America, now they could do the same thing on its own private database that is not a blockchain. They could use write-only records in their database, and it's a fairly common practice. Instead of deleting a transaction, banks will typically add a reversing transaction to maintain that history, but that's by convention. Immutability is built into the blockchain. Transparency, it's a questionable one. All transactions on the Bitcoin blockchain are public. So privacy is not necessarily a feature of blockchains. It has to be built in. Some blockchains have more security than others, but by default, the records are public. Now, can you make sense of those records? Can you identify that those records belong to one specific person? It's questionable. But some people made transactions on the blockchain, and if somebody's doing something illegal and selling those services, the FBI, other law enforcement agencies, they can look at the blockchain and they can try to piece together who is who's sending transactions to who. And so privacy is not necessarily a feature. Consensus is another feature. So nodes in a blockchain that are participating together will follow the same set of rules. And usually multiple parties have to agree that a transaction is valid in order to store that data on the chain. So what is this good for? Well, the first case, cryptocurrency, is one of the most prominent use cases today. Whether you like cryptocurrency or not, cryptocurrencies use blockchain technology. Digital goods. In-game purchases, for example. If you're playing a game and you want to buy armor or something that's going to make you perform better or something really rare, those transactions could be stored on a blockchain rather than going through an in-game store and having the in-game store centrally facilitate those transactions. Real estate is an interesting one. People have brought this up as a use case. It's not really used today as far as I'm aware, but it's surprising. When you go to buy a house, one of the things that you typically have to buy is title insurance, to make sure that your title, the thing that says, I own this house, is actually valid. It can happen that somebody shows up 50 years after you bought your house and you thought you're going to retire in that house, and they've got a piece of paper that says, this is my house. It's some parchment paper from 100 years ago that says somebody has a legal claim to your house. If we had blockchain technology, we could record those transactions in a way that's transparent, immutable, and we could prove that you own the house. It's hard to make that connection from the digital blockchain world to real world tangible stuff like houses or products, but it is something that people are investigating. Some have proposed that we do elections using blockchain technology. We don't want voting records to be tampered with. So if we stuck them on some kind of blockchain, we might be able to guarantee some kind of assurance that the data is valid. So far, though, a lot of people are still skeptical about this. Like, how do you provide privacy while still getting some of those advantages of blockchain technology? It's a tricky problem to solve, but people are looking into it. The blockchains are being used for supply chains, tracking physical or digital goods from, manufacturer, selling intellectual property, that kind of thing. There's a lot of potential use cases. Not all of them are necessarily a good fit for blockchain. Sometimes you can accomplish these same goals just using solid database technology, traditional databases, but it's definitely something that people are looking into. So let's create our own blockchain. We are going to manually create a blockchain with different transactions to show how blockchain technology works, at least to some degree. We're not going to have multiple nodes on a network validating these transactions. We are just going to show how the chain of data helps provide us assurance that the transactions are valid. So if we're starting a chain has to start with one link. This is sometimes called the Genesis transaction. And so we can take a look. Here is a Genesis transaction for this hypothetical blockchain that I just invented for this particular purpose. Here's our transaction. It's got a timestamp in the future. The transaction data just says Genesis. It's just a filler, essentially. It's the start, so there's no previous transaction hash. So the rules of this blockchain say to validate this transaction, we take a hash of the previous transaction and this transaction. So the previous transaction's hash, in this case, is just going to be a 0. Yes, I know it's not the full length of a hash, but this Genesis transaction will have a special rule in our blockchain. And the transaction data is Genesis. I provided a link there, that 0 Genesis link will take us to the cyber chef, where we will use the SHA-2 256 hash to hash this transaction. So what we're doing is we're taking the previous transaction's hash, that 0, and we are taking the current transaction data, Genesis, and we are computing the hash. So this transaction's hash is this BAE data right here. So that's the first chain on our block. So let's suppose, hypothetically, we've got a couple of people who want to use this blockchain to record data. So we've got Alice. She wants to send Bob $5. All right, we need to store this transaction on the blockchain. That's going to be the next chain in the link after the Genesis transaction. So let's take a look at that transaction data. What would this look like? We would have a transaction. We've got the timestamp of this new transaction. And here's the transaction data. It's going to say from Alice to Bob, amount $5. It's our very simple format. We've got the previous transaction hash. That was the hash of our Genesis transaction. So now we need to calculate the hash of this transaction. And I've got another link to the CyberChef there. I'm going to open that in a new window. And it'll compute it for us. So here's what we're doing. We're taking the previous transactions hash. That's from the Genesis block. Highlight it there. Okay, there's the previous transactions hash. And now we've got the current transaction data from Alice to Bob, amount $500. Sorry, I should have put a 500 there. I'll fix that typo in post-production. So we get the hash output here. It says, 8D1F. So we're using the previous transactions hash, generating a new transaction that incorporates the previous transaction's hash, that is what creates the chain of transactions. That's the chain in the blockchain, essentially. So we take this output here, we add it to this transaction data for this particular transaction, we record that on our blockchain. And we could just keep going this way, essentially forever. Our next transaction, Bob wants to send Eve $10. So we're going to add that to our chain. I'll open that in a new window again in the CyberChef. And so now as an input, how are we going to calculate this hash to continue our chain? Well, we've got that 8D1 hash from the previous transaction, the Alice to Bob transaction. So we grab that hash from the previous link in the chain, and then we hash the current transaction data from Bob to Eve. And then we get this output here, F691. That's the current transaction. We could just keep going like this forever and ever. The key idea is we use the previous transaction's hash to hash this data. Now, some chains, they might go back several transactions, 1, 2, or 3 transactions, just to provide extra assurance that nobody's been fiddling with stuff, that hackers aren't able to manipulate this data. So theoretically, what if somebody wanted to come back and modify one of the transactions in our chain? So I'll take this Alice to Bob transaction. What if somebody malicious said, you know what? Alice didn't send Bob $500. Alice sent Bob $700. So if we change that 5 to a 7, the transaction hash is different. Well, now all subsequent transactions that had relied on the, I'll call it the true hash, now their data is going to be messed up. People are going to look at that transaction and say, wait a minute. From Bob to Eve, that hash is now invalid. It doesn't match what is on the chain. So we can cryptographically prove that the data on the chain is valid, hasn't been tampered with. And we don't have to trust anybody. Our worst enemies might be on this chain. Malicious hackers might be on this chain trying to do bad stuff. But because hashing works really, really well, we can be fairly sure that these transactions are valid. So all the transactions are linked cryptographically so that the data cannot be modified. Now in this case, it's just us. We are just creating this data basically out of thin air. We have full control over our blockchain. So theoretically, I could go recreate the new Bob to Eve transaction, and I could record that on my private blockchain. But if I was doing this in a distributed manner, everybody else would reject that. They would say, no, 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 no. That is against the rules. We're going to reject that transaction. We are not going to store that on the chain. We're just going to delete that data because it doesn't match our consensus algorithm that we've created in order to validate transactions that go on the blockchain. So modern blockchains are often composed of thousands or millions of people all creating transactions, validating transactions, and that's how the data gets added to the chain. So will blockchain technology cure cancer? No, probably not. Will blockchain technology be the way that all data is stored in the future? No, probably not. Are there good use cases for blockchains? Yes, absolutely. A lot of people who are even skeptical of cryptocurrency still see blockchain technology as a somewhat revolutionary idea that could change the way that we carry out and store some transactional data worldwide in a decentralized manner.